Okay, welcome back, everyone. Welcome to undergraduate seminar. Logan Lim, one of my students in Math B42, is going to tell us why geometric algebra should be in the standard linear algebra curriculum. I'm super excited about this talk. I've been pitching it in all my classes. Logan, take it away.
All right, thank you. So about the word should here, this is a very strong word, so I hope to convince you on why I think that's the case. And it's going to have something to do with this little symbol right here, more specifically the cross product u times v. It's sort of a well-known thing that it doesn't really generalize well to dimensions beyond like 3, 7, and 9 and things like that. So we're going to be talking about like how we can generalize theorems, including the cross product, with some simple and really sophisticated mathematical tools, almost to the point of ingenious, I would call them. So let's just look at like our cast of characters in like standard linear algebra, because I want to sort of give you like this toolbox approach to the mathematics we're working with. So we have things that we see in our world like points. We want to sort of imagine like the concept of location, so we can distinguish one point from another. This is just sort of an intuitive notation of point. Points often have something called mass. Like, for example, if you're looking at a probability space, you have things like the mass of a point in like a discrete or countable probability space. So we also have things like lines, which have properties of length when they're finite. Things like planes that also have a finite area when we're not talking about the infinite plane. There's these things called parallel pipeds, which are like sort of these boxes. A really bad box, but. And we also have higher dimensional analogs. We can sort of imagine things like K volumes and such like this, right? And so in order to like conceptualize these sorts of objects, we use things called vectors, right? So vectors are these little things we think of as arrows, but really they're like choosing a one-dimensional subspace containing the origin of our set Rn and assigning them like a positive or negative magnitude. And so similarly, we have scalars, so just like the continuum, so negative infinity to positive infinity. And using these tools, we sort of conceptualize these objects up here with these vectors using notions of combinations. So say the combinations of vectors create a space. So this is like a three-dimensional space created for 3 vectors. We have subspaces. So we can have, say, a larger space, say like a 3-dimensional volume. And then we can have a subspace, say the plane. And importantly, the subspaces must contain the origin, right? So we have basis and span. So similar to linear combinations, this idea is we can have a finite set of vectors, v1, say v2, vn, that represents the whole space uniquely up to the scalar multiples, right? And we also have these angles that we often feel are important. And it's sort of related to the idea of orthogonality, the dot product, so on and so forth. And these geometric transformations, very important. Things like reflection, projections onto surfaces, say. And so these are sort of the main actors of linear algebra. And what I sort of want to argue is like in this toolbox, we can sort of have a better means of conceptualizing these objects and their algebraic operations without using matrices. And the advantage of that is it removes a lot of the complications from our algebra. Matrices are very powerful tools, but they're very general in the sense they don't always need to capture the algebraic relationships that have geometric nature of the objects like I described. So we're going to introduce something called bivectors. It's very parallelogram, so I'm going to redraw it. So bivectors are like these oriented segments of a plane. So just like a vector has a direction like positive or negative, right? If I multiply this by -1, it would go in the negative direction. Bivectors also have orientation. And it's sort of, you can think of it as like the direction that the cross product would take you in. That's the orientation of a bivector. It's like a representation of a plane. You're assigning like a scalar quantity to the subspace of the plane. And similarly, if we wanted to assign a scalar quantity to like a volume, we have these things called trivectors, which are also oriented. And we'll see why later. And I'll just draw these arrows to just really emphasize it. and we have higher dimensional analogs called k-vectors. And so I want to argue that that these objects right here, in fact, the sums of those objects can conceptualize all of these objects or all of these ideas and much more. So I'm going to move on with that. So I want to just step back and do like some sort of elementary justification as to what justifies like the sums of these k-vectors. So if we just think like in a very elementary way about vector spaces, like say we're counting objects, right? We're counting apples and oranges. So this statement is a statement sort of about, you can think about it as a statement of quantity, but I sort of want to emphasize that it's also a statement about actions, the action of counting. So if I were to say, label this 1, 2, 3, 1, 2, 3, 1, 2, and organize this by type, I would get this expression. If I were to say 1, 2, 3, 1, 2, 3, 4, 5, these numbers can be put into one-to-one correspondence, so it's equal to this expression. That's sort of what the expression means. We're characterizing the like sort of a transformation, not really in this case, but that sort of encapsulates the idea of vector spaces, right? We want to express like multiple elements in a single equation, right? Sort of related to the idea of a direct sum. So the problem with this example is like we have no idea what this means. It's not really a ring at all. It has no multiplication defined, and like thinking about -1 apples, like the analogy sort of breaks down. But I want to show you that the analogy doesn't break down when we talk about k-vectors. So this may seem contrived, but this is the same principle actually. The complex numbers and like say the real numbers, we have these elements that really can't be reduced in terms of each other, and so we have to, in order to treat them in full generality, we have to have scalar multiples of them or linear combinations of them. So here's a question. How far should we go with this? What kind of objects deserve this kind of treatment, right? And so I want to talk a little bit more about bivectors before I continue with the analogy. So bivectors, like I said, they're made from two vectors, and they are oriented and importantly shapeless representations of a plane. And it actually has a magnitude, like vectors have a length. The magnitude is the area of this parallelogram. So it has an orientation, an area, but it's a shapeless area. Does anyone, by the way, want me to go through like a quick proof as to why this is the area of the parallelogram, this equation right here? Yes, no? Thank you. Okay, I guess we'll move on. So this, you can just take my word for it. This is the area of the parallelogram. It's like a 30-second proof. You could probably figure it out by yourself. So now let's talk about these four tiles. Before we were talking about apples and oranges, it seemed sort of like weirdly condescending, right? But this is a better example. So what do we have here? We have like 25 floor tiles. So remember, vectors don't really, they can represent points, but they're not points, right? Because we can have a vector between here and here, but this vector is the same vector as this one, right? And in the same way, this oriented area right here, let's just say, because we're looking at it from down, that's the upper side of it. It's oriented in this direction. This would be the same vector, or I mean bivector as this. Since these are the same area, they have the same orientation, and they represent the same plane. And so you could sort of imagine us saying that we have 25 times this bivector, right? Because 25 is like the how much we're multiplying the area to get this, right? And if it has the opposite orientation, though, let's just call this bivector B. And I'll just put a little 2 there to remind you that's made of two vectors. And let's call this bivector C. In this case, since they have opposite orientations, but they have the same area, B plus C should be 0, right? They are opposites. C should be equal to -B. All right. So I want to sort of introduce you now to the driving force in all of this. The machinery that really makes all of this possible, all of these really great theorems, is this equation right here. And if you understand this equation very thoroughly, then you basically understand the basic idea of geometric algebra. So it's saying that if we have two vectors u, v, and Rn, we could perform sort of a multiplication between them. This multiplication contains an inner product and an outer product. And if you're used to exterior algebras, this will be very familiar. And yes, it is what you're expecting. This is the wedge of two vectors. And like I said, it has the area of u, v, theta. I should say magnitude. This is stuff from Math B42. Yes, exactly. Thank you. In particular, so this goes to just the wedge product because the inner product vanishes if these are orthogonal. So let me just remind you, B1, B2, orthogonal if and only if this is 0. And we're going to assume all of these vectors are non-zero. So just keep that in mind. So the main idea of geometric algebra is to represent these subspaces of Rn with algebraic objects in this new special set called Gn, which is an extension of Rn. So if the bivectors, or sorry, not bivectors, if the vectors B1 to Bk are orthogonal, then dot product is 0. And so this becomes just a wedge product. And we call these objects k-blades. And so they represent geometrically these things like our arrows, our floor tiles, our boxes, boxes, etc., as geometric objects of this Gn. And we have this also very special element called the n blade, which is just when k equals n, the maximal dimension of products you can make. Yeah, I think it's a little confusing terminology, but I've grown to like it a little bit. So basically, then it's called a pseudoscaler, which is very, very important in geometric algebra because it sort of represents the idea of an orthonormal basis, which we'll get to later. It's very cool. So what is Gn? Gn is actually a 2 to the n dimensional vector space formed from Rn by defining the geometric product. That's really what it is. So if we're talking about G3, let me just write out all the basis elements here. So we have the scalar, 0-dimensional one. We have the one-dimensional objects, which are the actual vectors itself. This is the orthonormal basis, by the way. B1, B2. From now on, this will be an orthonormal basis. And then we have these things called bivectors. This should be E1, E2, E3, E1. And then we have a single trivector, 1, E2, and E3. So this is dimension 1, dimension 2, 3. Remember, scalars sort of represent like these 0-dimensional objects. And strangely enough, so does this. This is a 0-dimensional object. It represents the entire set R3 itself. This represents like the 0 vector, that subspace of R3. And this represents the one-dimensional subspaces, which are lines, two-dimensional subspaces, which are planes. Right? And oh, if you count all these, this will also be 2 to the 3, which is 8. Went back to 0 dimensions in B42. Sorry, I'm not sure what you mean, but I have to move really quickly to get through everything, so I'll address things later. So for an orthonormal basis, E1 to En, so we have these things called multivectors, and this is in general. So this is a lot to take in. This is just a vector. Notice that it's just a sum of scalars times these orthonormal basis. So vector, this is a scalar. But this is actually the k-vector parts of this multivector. And this is actually the standard notation that you're supposed to use. What I showed you here was that this notation that I just use for my own convenience. I haven't seen it anywhere. So when I think of a scalar, I think of it as like a 0-dimensional vector. So this would just be some A and Rn, or sorry, just some A and R. So the vector B1 would be in R2. I just find that just makes it easier for myself to conceptualize. And so we have this theorem that G to the n is a 2-dimensional to the n-dimensional vector space extended from Rn. Right? And so, okay, why do we even care about this? Why should we even do this? So let's look at like this set of numbers that's maybe sometimes useful. I don't know, ask a physicist. So we have these numbers. We have two scalars a, b, just real numbers. But we have this element that squares to -1. And that's really what enables us to talk about complex numbers. It's part of the axioms of complex numbers. So if we find that this statement is satisfied, then we can call whatever set satisfies it the complex numbers, right? It's just like a part of axiomatic mathematics. So here's something weird. This is a bivector, right? E1 and E2. Let's just say this is E1, this is E2, they're the same length, orthonormal basis. So this bivector is like a representation of this oriented area, right? And the inner product is 0 since they're orthogonal, so this just becomes the wedge product. And what happens when we try to square this? This is a perfectly valid operation if we assume there's closure in this set, right? So if we square this object, we can actually rearrange the terms of the cos the negative sign, which is a property of this exterior product, Ej is equal to Ei wedge Ej, right? And here's one thing I haven't mentioned before. Ei squared, for now, equals to 1. And so we swap all the terms, reduce them, and this quantity is actually equal to -1. Weird, right? So if we let a and b be real numbers, and we choose all numbers in the set Gn of this form, again, these are just scalars, a and b, then this is actually isomorphic to the complex numbers. So the complex numbers are a subalgebra of Gn. They are a special case of Gn and have a better geometric interpretation of this frame. What does that mean exactly? So why can the complex numbers so effortlessly represent rotations? So the answer that geometric algebra gives is because there's actually an element that represents the plane on which it is rotating. And so let me show you what I mean. So let's say we have two vectors u, v, and Rn, and we have this thing, the unit bivector containing u and v. So basically, if we have the bivector of u and v, it's like this. And basically, the only thing we have to do to get the unit bivector is just divide it by its magnitude. That's it. As long as this doesn't have 0 area, so it doesn't collapse to 0. And so let's look at what this product actually means now. So the inner product is, of course, u times v cos theta. And the outer product, area of the parallelogram, should be u v sine theta. And this term I is the unit bivector representing the plane containing u and v. And so you could factor it into this form and then create this form. Pretty cool, right? So this means we have the identity uv is equal to magnitude of u, magnitude of v, e to the I theta. And in fact, we call this the angle, e I theta, where I is a bivector. Let's see that. So that means in geometric algebra, every bivector, and as a result, every plane is a representation of the complex numbers. That means we could perform rotations just as easily in the complex numbers, but it's even better, and I'll show you why. So I hope you can see now, associating these positive and negative quantities to the subspaces of Rn, and then allowing vector multiplication is like some really mind-blowing fact, and it generalizes a whole bunch of areas of mathematics. I can't even go through all of them because there's so many. So let's look at what it actually takes to rotate in general and dimensions. So let B be a blade, so a product of n vectors, of course. Suppose we want to rotate this blade by angle theta on a plane represented by the bivector I. So I'll just draw some sort of plane here. I call this I. So for any blade B and any angle I theta, this is the rotation. That's it. If you've tried to do rotations before, this might really shock you, because rotations in Rn are a notoriously difficult thing. If you don't mind, I want to show you a paper. How do I show my screen now? It doesn't seem to be. Oh, I have to stop share here. And then I want to share with you this. This is the linear algebra way of rotating things in n dimensions. So I have a question for you. Do you want to do this, or do you want to do this? Like, you can see which one's more ergonomic, right? And in fact, you don't have to have any special like matrix algebra to do this rotation. You just have to, once you've already defined the multiplication, you've defined this exponential notation, you've defined blades and all the multiplication, you don't have to do anything else. This is it. That's all you need to do for rotations and dimensions. Not only that, it's for any blade. It's not just for vectors. It's for planes, it's for volumes, it's for hypervolumes. This formula encapsulates all of that in one notation with one product. Vectors are just a special case. So now let's talk about more about the pseudoscalar. Before I said the pseudoscalar sort of represents the orthonormal basis of the subspace, or sort of the regular space, the entire space. So in G2, this is one unit pseudoscalar. E1 and E2. Actually, I should say it's the pseudoscalar because I don't think there's any other coordinates in here. So that's like the representation of the plane. Note that the quaternions don't contain the unit pseudoscalar, which is E1, E2, and E3, because they can be expressed as these products, E2, E3, E1, E3, and E1, E2, the bivector basis of the space G3. It's often called the even subalgebra of G3, the quaternions, I mean. So why are they called pseudoscalars? Before I showed you this sort of Pascal's triangle looking construction, where choosing combinations of these basis vectors E1 to En. If you choose M of them, you could actually form, using the combinations, the linear combinations, you could form all possible subspaces. So for example, if we're working in G3, there are three bivector elements in the basis, E1, 2, E1. So it's a result of choosing three of these component vectors in G3. And we can form any plane from that representation. So every subspace of our two-dimensional subspace of R3 can be represented as a linear combination of these. And so that's another reason why the dimension of Gn is 2. So these are called pseudoscalars because they are basis for a one-dimensional subspace of Gn. That's like thinking of Gn as its own vector space. Just like the scalar elements of R are, because again, the site combinatorial identity, n choose 0 is equal to n choose n equals to 1. And similarly, we have pseudovectors, which are n-2 blades, so products of n-2 orthogonal vectors. So the dual of the multivector, this is why this is so important, pseudoscalars. What happens when we invert the pseudoscalar, which means just reversing all its elements, we get the inverse of that pseudoscalar. And if we multiply it by a blade B, some of you may be already familiar with this, it actually gets you the orthogonal complement, the blade that represents the orthogonal complement of that subspace. So no matrix algebra there. If you're familiar with exterior algebras, you may know this is the Hodge star. I'm not sure if it's always related, but I think it sort of takes the place of the Hodge star in that algebra. But for this reason, the dual of the outer product is actually the cross product. So what does that mean? So say we have this bivector here. It's oriented in this way. Say it's UV. And actually, the dual of this would be this vector, right? That's the orthogonal complement. But more generally for multivectors, it's this formula here, but I don't want to get into it because it's a little more complicated than I'm intending. But here's some housekeeping. So before I just said, okay, assume this was true. So we could get the result E1, E2 squares to -1. But not everyone wants to do that. There's very good reason for that. So if we decide that this squares to 1, we get something called the split complex numbers. If we decide it squares to -1, it goes to the complex numbers. If it squares to 0, it goes to the dual numbers. So what are these? The split complex numbers are represented by, I think, number j. I'll just say this is I and this is epsilon. So say we have two scalars a, b. So a plus bj is the split complex numbers. A plus bi is the complex numbers, and a plus b epsilon is the dual numbers. So the dual numbers, they square to 0. Complex numbers square to 1. Or sorry, -1. And split complex numbers square to 1. So what are these used for? This is used for like a standard Euclidean space, the split complex numbers. But be careful because like if you take the norm of a plus b epsilon, or sorry, not epsilon, that should be j, equals to 1, you actually get the unit hyperbola. And not like a circle. I believe that's right. Yeah, I think so. Yeah, so these sort of represent the hyperbolic, elliptical, and Euclidean transformations in the space. And they're used for projective geometric algebra and space-time algebra, which is another endeavor to bring geometric algebra to physics. And I'll speak more about that later. And so there's this video, SIGGRAPH 2019, highly recommend, especially if you're like a more computer science-minded person. And so if you want an algebraic reference, though, there's some notes at the end that you may be interested in. So here's one advantage of this formalism, linear independence. You remember it's like a whole thing in linear algebra, a whole bunch of proofs require linear independence and are about linear independence. But remember, if u and v are orthogonal, we have a dot product equal to 0. However, with the outer product, we know these are linearly independent so long as this outer product of these vectors does not go to 0. Kind of interesting, right? So the orthogonal complement, like I said before, we were talking about the dual of a blade. So I just want to justify briefly why this is true. So say we have this vector u, which is like a sum of this orthonormal basis b1 to bn. So if any of these are non-zero, then this outer product can actually be distributed into the sum. And then we could swap at the cost of a negative sign until we get something like this, bj and bj, which evaluates to 0. And so this entire sum goes to 0. And so if this is a linear combination of those vectors, that entire thing goes to 0. And so I'm just further emphasizing that if u is in our subspace, we have the outer product of the blade goes to 0. If it's in the orthogonal complement, then the dual of the inner product goes to 0. And this is the more precise reason that we think that blades represent subspaces, because we can actually test, like as a first class algebraic operation, whether they're or not they're in the subspace, which I think is super cool. And determinants also become fundamental with this framework, because let's say we have this matrix of x1, x2 to xn in Rn, that's important. If we take the outer product of this, it's actually equal to a determinant times the pseudoscalar of the space. So the determinants are also fundamental. And this actually simplifies a ton of the determinant proofs in linear algebra. It's one of the reasons, like I'm saying, this should be in linear algebra, is because so many of the proofs just like become almost trivially simple, like when you include this framework. And we'll see a lot more of that in just a second. 3 minutes, good. Okay, so let's talk about. Am I not hearing something?
So just back one sec.
Oh,
is there an interpretation for the determinant as a volume of the thing?
Oh, that encapsulates. This is a generalization of that. So if it's a volume, x1 and x2 and x3 is equal to the determinant of say a 3x3 matrix. Times I3, which is the unit pseudoscalar of In. And it's unique up to, this pseudoscalar is unique up to scalar multiplication, which is why one of the reasons why we can do this. And so yeah, the 3-dimensional volume is the special case.
Nice, super duper cool, thank you.
So I want to talk about manifolds. So look at, this is the surface of an apple, say. So we can look at every point on the surface of this apple with a parameterization. That's what I mean by these wrapping UV vectors. And so you can sort of imagine that we want the tangent space on this surface. So what's a tangent space? We have a bunch of tangent vectors, right? If we extend those tangent vectors out with scalar multiples, we get something called the tangent space. So in this case, it will be a 2-dimensional tangent space because it's a 2-dimensional surface. And in general, if you have an m-dimensional manifold, you have an m-dimensional tangent space, so same dimension. And using this, we could actually generalize a lot of the integral theorems in multivariable calculus. But that's not it. We can also do something like this. We can have vector fields that include scalar elements, vector elements, bivector elements, and trivector elements, all in our formalism. And so our statements can actually contain a lot more information than normal. So I want to show you this. This is actually not a definition. This is a theorem. So it says that for a differentiable field f on our manifold, say the apple we were looking at before, into Gn, the gradient of f, this is the geometric product, remember, is equal to the divergence plus the curl. And again, we're defining this in terms of the wedge product because this cross product doesn't generalize to multiple dimensions, but it's dual to the outer product, which does generalize to multiple dimensions. And I have absolutely no time to explain all of this in detail. Like, I'm basically giving you the Snape kills you know who of geometric algebra. So like, this is going to be very rough and fast. So this multi-vector integration directed integrals, things like line integrals, surface integrals, and higher dimensional analogs are all consequences of this. So this is like this big fancy X is a parameterization of these terms U1 to UM. And so it's saying that the infinitesimal pseudoscalar geometric product with the vector field is equal to the actual outer product of these partial derivatives with of this parameterization with respect to each of its components. And so it sort of replaces the cross product in the definition. So this dm is the pseudoscalar in the tangent space, T of P. And P is a point on a manifold, of course, times the infinitesimal m volume, d to the mx. And so, which brings us to like the biggest theorem. Well, it's arguable. There's a lot of big theorems. So if we have an m-dimensional oriented closed and bounded manifold with a boundary partial n and a continuous field over the manifold and the boundary, we have this result called the fundamental theorem of geometric calculus. This is actually a generalization of the things called the divergence, curl theorem, and gradient theorem, which are generalizations still of Gauss's theorem, Green's and Stoke's theorem, and the fundamental theorem of line integrals. And actually, there's this book I'm going to recommend at the end called Vector and Geometric Calculus by Alan McDonald. He has a whole chapter. Basically, he starts out, oh man, I hope I can find this fast enough. He has a whole chapter. So he puts this statement at the very start of the book, and then he spends a whole chapter re-deriving as special cases all of these theorems. So it's very, very cool. And something important to note is the Cauchy integral theorem also generalizes in this way. So I think he says in the book, like, this means that real analysis and complex analysis essentially become a single subject under this framework. So here's something that's of importance to physicists, but I'm going to be disrespectful and call it the mathematical party trick for our purposes. So Maxwell's equations in electrodynamics actually become Maxwell's equation. How is that possible? So E here is an electric field. So it takes a time parameter and it takes a point in R3. So let's just say X, Y, Z. And this is actually a vector field like in typical multivariable calculus. So I think it's R4 to R3, is that correct? And then we have this bivector field, also taking T, X, Y, Z, representing the magnetic field, gives us back bivectors. I'll just use this notation. I think many are familiar with it. Goes from R4 to this. And so again, conceptualizing the curl without the cross product gives us a lot of higher dimensional analogs and sort of algebraic ability, right? So we can reduce all these four equations in terms of the geometric product. So this little partial t is like the teeth component of the derivative. So it's by del t. That's what it means. And so all of these equations, which you'll just have to trust me, are Maxwell's equations, become this formula. That's because when you use the geometric product, all this expands to these. Just simple identity. So why maybe have you not heard of this before? So this is actually a pretty old subject. It's been around for maybe 100 years or so. And long story short, Clifford's work didn't really become as well known among mathematicians as people like Gibbs, which is why we use matrices for everything now. But like, there's a ton of different geometric operations that really don't need the full expressiveness of matrices. Matrices are still powerful, and we definitely need them for things like representation theory as well. But there are better ways of conceptualizing these algebraic relationships with geometric objects by just including like an extra assumption of the geometric product. And so in this paper, the vector algebra, where they say, we thus historically review the development of various vector systems and conclude that Clifford's multivectors best fulfills the goal of describing vectorial quantities in 3 dimensions and providing a unified vector system for science. Basically saying, this is the best thing we know out here right now that we could do these operations with, in science at least. So like, okay, you might think this is all well and good, but how do we practically start getting into Gn from our real n-dimensional real numbers? Really, it's only one thing: closure under the geometric product. Remember what I told you? That's it. That's all you need to know. Well, I'm sort of lying. There's also one more thing you need to do. You need to stipulate what this is, because that's actually a feature. If you want like hyperbolic transformations, you want elliptical transformations. For example, I think projective geometry is something like, or 2D projective geometry, something like this. 3D projective geometry, something like this. Oh no, sorry, this is like space-time algebra. This being like 3 elements that square to 1, 0 that square to -1, and 1 that squares to 0. And the one that squares to 0, for example, in space-time algebra is the time dimension. Okay, and if you want a short and bare bones elementary construction, something that's like a couple pages, you can see reference 6. So when should this actually be taught? Like, it's all well and good to say it should be taught, but we should think about where we should insert it into the curriculum, right? So my belief is that it's simple enough to learn after the dot product. And not only that, we can actually define the dot product in terms of the geometric product. So we don't even need to stipulate like its existence. We could say this, and also the outer product can be put in terms of the geometric product. This is another reason why it's called the symmetric and anti-symmetric part of the geometric product. So this statement, like you understand what a plane is, you understand what a parallelogram is, you understand what angles are. Like that means you probably can understand what a bivector is. And so this statement is simple enough for first-year students, but leads to a generalizable framework for complex numbers, quaternions, all of these integral formulas, all of these rotations, projections, and like I haven't even shown you projections. So say we have like a blade B, we can actually project onto that blade B from a vector u by just doing this. That's it. And if we want to find the rejection, which is to say the vector that's orthogonal to you in the subspace V. So say, let me draw a quick diagram. This is u, and this is our subspace B. That's u, the reject of u, and this is the perfect u. So this would be, oh no, sorry, I think I have this backwards. So PB u, no, I think this is right. I think I'm getting confused, a little bit confused here. But in any case, this is equal to u and v, and over, sorry, u and v over. All right, I think I might be getting the order switched up here, but it doesn't matter for our purposes right now. So if you want to test your understanding of this actual subject, here's the most important thing you need to know. This calculation right here. If you could do this, I think you can understand the rest of the subject. So let's say we have 2 of these vectors, uv and R3. And so we just give them these coefficients. If we multiply them, what we get is this big summation and these sums, which are as part of the bivector basis. And if you look at these really closely, you'll notice something. This is actually the inner product of the 2 vectors in Rn, and this is actually the cross product times E3, E2, and E1. So if you want some more introductory material, here's one thing I suggest. There's this great video in Manum. I'm pretty sure all of you guys have heard of 3 Blue 1 Brown before. So he made this great math library, and a whole bunch of math animations were like created from it. And so one person is making videos about geometric algebra using that library. And if you want a more historical perspective, you could look at David Hessinus. He's like one of the pioneers of applying geometric algebra to physics. And he's like one of the reasons why there's such a huge push by physicists saying, wow, this is so awesome, because he sees like all the applications to like the Pauli matrices and like a whole bunch of different areas in physics all just collapsing into a single thing once we assume this very simple operation exists, right? So the recommended, do I recommend any textbooks for undergraduates? Well, I already showed you this book, right? It's called Vector and Geometric Calculus by Alan MacDonald. I think this is, since it's a very new subject, this is probably one of the only textbooks that exists on the subject. There's lots of like small papers on it as well you can find online. There's also another book called Linear and Geometric Algebra by the same one. But here's why I like them. He also has an associated video series that explains all the concepts. Like they're very short as well. They're short, they're cheap, concise, and filled to the brim with exercises. Like, I'll be honest, like when somebody asked me to buy a huge, like 200-page, not 200 pages, but like a 500-page textbook that's like this thick, I know I'm not going to read it, but this, you could read this in a month. Like this is fine, and it's full with a bunch of exercises. So I like them. I definitely recommend you buy them if you're at all interested in the subject. And it has like a whole bunch of comparisons, like to classic linear algebra, classic vector calculus. There's like tables for differential forms. There's everything. These are great books. I love. Also, I want to show you a website called Bivector.net. I've included the color palette on this thing, but let me just show you what this website is about. Can everyone see my Firefox? Can everyone see? Okay, good. Let me just zoom. So Bivector.net, there's these, I talked about the SIGGRAPH 2018 talk. There's these two people called Charles Gunn and Stephen DeKinnick, and they made this website, maybe I think with one of their other colleagues, all about geometric algebra. So it has like a whole bunch of videos, a whole bunch of code even, and animations about geometric algebra. Some of the videos are pretty advanced. You need to know a lot of geometry, maybe even algebra, to understand like Stephen DeKinnick's talks, but it has more simple things as well. So it has all of these animations that were actually built with geometric algebra, conformal geometric algebra, projective geometric algebra, how they relate to their subalgebras, and something so cool. I just find this so amazing. So we look at the code. This is what I'm looking for. Tools. Oh, yes. So you could actually type in a signature for the geometric algebra you want to generate, and it will generate code for you. So you don't even have to create all of those operations yourself. So say, for instance, I could, this is 3D projected geometric algebra, 3 positive dimensions and 1 0 dimension. And I could choose the dual numbers, which is this. And it shows me the Cayley table of all of the elements as well. So we know how to connect them together. And we could choose custom ones. And we can also download these things, which are like generated code samples of all of the multiplication operations. So you don't even have to do them yourself. If you don't, you're like, I can't be bothered to like write out all of these computations, then this generates it for you in Rust, C++, C#, and Python. Wow. All right. So I'm going to move on. Yeah, so that's it. There's my references. And did I make time? For some reason, I can't really see the chat. Oh, there. Oh man, I missed so much chat. I'm sorry, guys. I can't really hear you, Professor Parker.
Oh, sorry, folks. People couldn't hear me there. I want to say that was an amazing presentation. That was very, very fast, very, very amazing. You made time. Before we get into questions for our speaker, I would like to ask people to take 2 minutes and fill out the seminar feedback form, which is there. Logan's done a lot of speaking, so if you want to take 2 minutes and have a glass of water, Logan, we'll resume with questions at 2:51.
if you guys want to see any slides in particular, again, don't be afraid to ask. I'll just take a quick peek through them just in case anything comes to mind.
Yeah, I like this stuff a lot. The application, that last calculation was particularly great. That like just the dot product and the cross product show up super duper naturally. That was very cool.
It's so mind blowing, right? Because like the connection to complex numbers, I think. Because I remember when I was first studying linear algebra, I had this thought to myself. It's like, okay, we can multiply vectors with the dot product, but why is there not like some other multiplication with vectors? I'm pretty sure everyone's had that thought before, at least once. It's like, why is there no multiplication across vectors? It seems like that would be a natural notion, but it's sort of absent from our current curriculum, where you can enter the signatures. Oh, sorry, it's on the presentation slides, but I will also send them here.
So I'm going to stop the recording here and then open up the floor to questions. I also have to run and teach. I'm going to go teach A22, and I will tell them about Clifford algebras. Okay, maybe not today. Maybe in a future implementation of the course. But yeah, that was a solid pitch for Clifford being included in Clifford Grassmann algebras being included in linear algebra. So thank you very much. That was absolutely awesome. I'll stop the recording here.